Hello, I want to show a couple problems here on using the DeBroglie wavelength equation and the uncertainty principle. So let's start with the DeBroglie wavelength. So we can write that the natural wavelength of matter is equal to Planck's constant divided by the mass of the particle times the velocity of the particle. And so let's consider here an electron with a velocity of 3.00 times 10 to the 6 meters per second. And let's go through the steps to try to calculate what the DeBroglie wavelength will be equal to. Now the mass of one electron is 9.109 times 10 to the minus 31 kilograms. This is a given, and the velocity is also a given. So I don't expect you to know the mass of the electron off the top of your head. Expect that to be provided to you if you need to do a calculation like this. And so the way this will go, we'll take 6.626 times 10 to the minus 34 joules times seconds, divide that by 9.109 times 10 to the minus 31 kilograms, and then times 3.00 times 10 to the 6. Now let's think about units for a moment. A joule is a kilogram meter squared per second squared. E is equal to mv squared. So you might remember those units. And then time seconds. So this here is just the joule, and then joules times seconds. So I've rewritten my units here. That shows me I wanted the mass to be in kilograms. Luckily it already was in kilograms, but if we had a mass in grams or some other unit, we'd have to convert to kilograms. And then the velocity in meters per second cancels, and also the joules times seconds cancels. So we cancel one of the second units, and then we cancel the other. Then we cancel one of the meters, but not the final. So we get a wavelength unit out, so we get a unit of length in meters. If we throw this into a calculator, we should get our numerical result, 6.626 times 10 to the minus 34, divided by 9.109 e to the minus 31, and then divide by 3.00 times 10 to the 6. That works out to be 2.42 times 10 to the minus 10 meters. So, let me actually rewrite that. So what this result is showing us of 2.42 times 10 to the minus 10 meters, 1 meter is 10 to the 10 angstrom. So we can multiply this 1 meter by 10 to the 10 angstrom and see that this is 2.42 angstrom. So the uncertainty for an electron at a somewhat normal velocity for an electron is on the order of the size of the atom. It's actually bigger than the radius of even like a carbon atom. So in other words, this is a pretty big wave, or this is a relatively large wavelength. So the motion of the wave is on the order of the size of the trajectory of this electron spinning around an atom. So the idea here, you have an electron, you have an atom, electron spinning in a wave-like behavior around the atom. Now, interestingly enough, it's that wave-like behavior that's going to lead to the notion of energy levels. So why we get N1 and 2 and 3 and 4 from the Bohr model ends up being, that we need a replicating wave, and what's going to increase are the number of nodes, if you will, or wavelength cycles, but it's really the wave-like behavior and the Bohr-type model that give us this picture of the electron spinning around with a wave-type pattern around the nucleus of an atom. Okay, so plug in your units, track your joule is a kilogram meter squared per second squared, so you see your mass needs to be in kilograms in problems of this nature. Okay, let's take a look at an uncertainty principle problem. So we know our equation for the uncertainty principle is delta x times m delta v is greater than or equal to h over 4 pi. Okay. What x is standing for is the uncertainty in position Think about an electron firing from a negative potential across to a positive. There's some electron on its way from one potential to the next. So it has some location, and then it has some velocity. And then these have some uncertainties associated with them. So you can think of the particles being some location x with the plus minus for the uncertainty in the x on where the particle is located. Then it has a velocity and some uncertainty in that velocity. Mass is the mass of the particle. Now, often we do this calculation for electrons, or electrons are the smallest subatomic particles, so they are the particle that have the most uncertainty and position and velocity simultaneously compared to like a large object. But we can use this equation for large or small objects. It just only becomes really an issue for describing the simultaneous position and velocity of a really small particle like an electron. And so delta V is the uncertainty in velocity. And so if we have a velocity, we said earlier we had a velocity in that problem of 3.00 meters per second. Well, think about the uncertainty here, because it's really this plus or minus that is our uncertainty that is of note within this particular problem. So V would be 3.00 times 10 to the 6. Delta V in this example is just that plus minus. It's the uncertainty. It's how uncertain we are in the velocity. Okay, so I would just write it 0.05 times 10 to the 6. So if we have an electron with this uncertainty, or if we have an electron with a velocity of 3.00 times 10 to the 6 meters per second, and our uncertainty in that velocity is 0.05 meters per second, then the way we would solve for the uncertainty in x, if that's what we want to solve, then it's going to have to be greater than or equal to h divided by 4 pi m delta V. Okay, so we're still considering the electron here. We're still considering as a given, it's 9.109 times 10 to the minus 31 kilograms. Again, you wouldn't have to memorize that. We're just using the same numbers from the previous problem. The let me move this over a little bit. Okay, so let's plug in. So 6.626 times 10 to the minus 34. Now I'm going to just do the kilogram meter squared per second squared for joule right off the bat, times seconds, divide by 4 pi, no units there. 9.109 times 10 to the minus 31 kilograms. Kilogram cancels, and then I'm going to plug in the uncertainty in the velocity, 0.05 times 10 to the 6 meters per second. Okay, so the minimum uncertainty in the position also comes out with unit of meters once we cancel out our seconds and one of the meters. So we get a unit of length out for this problem as well as the previous one. So we go 6.626 times 10 to the minus 34, divide by quantity 4 pi times the mass of the electron, and then times 0.05 E6, end parentheses, calculate. So my calculator says 0.00001. Now, I could do a few things. Probably the easy thing to do is to do like a second scientific mode. So I get 1.16 times 10 to the minus 9 meters. Now my uncertainty is actually just the ones placeholder here. So this would just be 1 times 10 to the minus 9 meters. I'm going to go to angstrom as well. 1 meter, 10 to the 10 angstrom. That gives me, I'm going to go back to my floating mode, 12 angstrom. And if you round to proper sig fig, so we'll just say 10 angstrom. We only have 1 sig fig in our uncertainty. So 10 angstrom of uncertainty and where that electron lies. So what we have for the electron is a particle that's behaving like a wave from the DeBroglie wavelength, and then a particle where we don't exactly know where it is at the moment we know its velocity. Now think about your analogy to a baseball. Like a baseball, you know the mass of the baseball, pretty well. I think it's 0.145 kilograms. I could be wrong. I'm just remembering from an example I used to do. But for a baseball, let's say it has 100 miles per hour, or like a really fast fastball. That's still only like 40 or 50 meters per second. That if you throw those numbers into here, the uncertainty you might have in the velocity, if you plug it in as like plus or minus 5 miles per hour, do the conversions into meters per second. I mean, I don't even care about doing the problem. The point of this isn't to do a tricky conversion problem, but it's just to see that the relative like ordinary velocities and the ordinary mass mean that you would have virtually no uncertainty in where that baseball is at any given moment. That it's only when you have a uncertainty that's relatively high in a way, like, so when that's relatively high, and whenever your mass is relatively low, then we're going to end up getting a big uncertainty in our position. Now what this is going to lead to is just why we discuss orbitals for atoms instead of a discrete solving something like the Bohr model for our larger atoms. So we're going to move in and talk about orbitals on Tuesday, talk about electron configurations as we wrap up chapter 6. All right, I thought I would give a couple videos on these problems here in case you encounter any problems like this over the weekend so you can move past solving these types of problems. All right, have a great weekend.